All right, here's the last few problems from the midterm of Math 151 in the, what is this, fall of 2018. Taking the derivatives, just take the derivative of these functions. Right. First, on this one, you got to realize this, the notation, tangent cubed of something means take the tangent of that thing and then cube the result. So when I'm taking a derivative, it's first and foremost a cube. So I need 3 times that stuff squared. So 3 times the tangent of whatever squared. So 3 tangent squared of this thing. Then I got to take the derivative of the inside. Well, the inside is a tangent of something. So the derivative of the tangent of something is the secant squared of that something. And then I need to take the derivative of the inside of that, which is the derivative of that polynomial, which is just 6x squared. So the grand total, you've got 3 times 6 is 18x squared. You got a tangent squared of 2x cubed plus 3, and you got a secant squared of 2x cubed plus 3. I saw bits and pieces of this in a lot of people's answers, but very few actually navigated this completely correctly. It is a something cubed. So the derivative is 3 times that something squared. Then handle the derivative of the tangent, secant squared. Then handle the derivative of the inside of that. Okay. This one I was pleased to see only a couple people did it wrong in a particular way. There's people who look at this and say, "Oh, product rule." It's like, no, this is not a product. This is the log of something. There's going to be a chain rule in here. Right? So taking the derivative of the log of something is 1 over that something times the derivative of that something. And the derivative of the cosecant of x is minus cosecant x cotan x. So derivative of the log of something puts the something in the bottom, then times the derivative of the inside. And then plus the derivative of the hyperbolic sine of x, which is the hyperbolic cosine of x. It just so happens that the cosecants here cancel out, so you get minus cotan x plus hyperbolic cosine of x. Number 16 was a little trickier. Some people said, hey, I'm going to use a power rule. Some people said, I'm going to use an exponential rule. You need to do neither of those. Actually, you need to do both. But the way we've been doing this, something like this, is logarithmic differentiation. Take the log of both sides. So the log of y is the log of y. The log of this thing, I can use a property of log then and take the 1 over x out in front. Now implicitly differentiate. The derivative of the natural log of y is 1 over y times the derivative of y. And on this side, I've got a product rule. So I've got a 1 over x times the derivative of the log of sine x. So the sine x goes on the bottom and the derivative of sine x goes on the top. And then I have the second times the derivative of the first, and this is an x to the minus 1, so its derivative is minus 1 x to the minus 2. Right, so I've got something like this. I can then multiply both sides by y, and I've got the answer. So when the y comes up over here, that's it right there, because remember y is sine x to the 1 over x. And then all this stuff is the stuff in parentheses here. Cosine x over sine x I wrote as cotangent x. Right? But logarithmic differentiation is the way to go with that. And on to the last page. If I can flip the page. Here we go. Find any equation of the tangent line to the graph given by this equation at this point. Okay, so I need to know the equation of a line, so I need to know a point that it goes through. Got it. And a slope. Well, to find the slope, I'm going to have to find the derivative at this point. So I have to do this implicitly, taking the derivative of both sides with respect to x. This gives me a 3x squared. This gives me a 6y times dy dx, or y prime. There's a product rule on this one, so the derivative of x times y, so 1 times y, plus x times the derivative of y, which is right there. And then the derivative on the other side is, derivative of that constant is 0. Solving for y prime now, so I subtract the 3x squared over, I subtract the y over. I'm going to factor out a y prime, which leaves a 6y plus x, and that then gets divided into the denominator there. At the point 1, 2, I can plug it in. Plug in a 1 for x and a 2 for y, a 1 for x and a 2 for y, and I end up with the slope is negative 5 over 13. So the equation of my tangent line is y minus the y coordinate I want, 2, equals the slope times x minus the x coordinate that I want. And if you multiply that out, it looks like this. I prefer the answer looking like this one here, but a lot of people multiplied it out, wrote it like that. Okay. There were a few little things that went wrong here. People missed that product rule. Sometimes when people factored the y prime out, where this is 6y plus x, they had 6y times x, so this plus turned into a times, which threw off that. Anyway, there were some minor things that went wrong there, but anyway, implicit differentiation to find the slope on that one. 18, use logarithmic differentiation to find this thing. When you take the log of this quotient, it's going to be the log of the top minus the log of the bottom. But the log of the top is the log of a product, which turns into the sum of a couple of logs. So you got the log of the first one plus the log of the second. But that first one has a log of something cubed, and the 3 can come out in front. Likewise, in the denominator, this is the log of a product, so it's going to be it's going to be minus a whole bunch of stuff in parentheses, and the minus sign I'm distributing, because this being the log of a product would be the log of the first one plus the log of the second one with the minus sign distributed. And that first one, again, has that something cubed, so the 3 can be written out front. So the log of the right-hand side is this. It's no longer a quotient and product. It's now a sum and a difference, which is why we choose to do logarithmic differentiation. We turn quotient rules and product rules into sums and differences, which are so much easier to do, right? But we got to deal with the logs too. Now, take the derivative of both sides with respect to x. The derivative of the natural log of y with respect to y would be 1 over y. But with respect to x, you got to multiply that by dy dx. So there's that 1 over y prime. Taking the derivative of a sum now is really nice, because I'm just going to do each part. This 3 comes along for the ride. The derivative of the natural log of something is 1 over that something, so there's the 3x plus 1 in the denominator. The chain rule then says multiply by the derivative of the inside. Well, the derivative of the inside is 3. So I got the 3 that was already there, and now times another 3. Likewise here, the derivative of the natural log of this thing is 1 over this thing times the derivative of what's inside. That's the chain rule, right? The 2 comes out. This one right here, the minus 3 comes along for the ride. Derivative of the log of this thing is 1 over this thing times the derivative of that thing. And the derivative of x squared plus 4 is 2x. So there's that. And then I've got, similar here, the cosine goes in the bottom. The derivative of the cosine of x is minus sine x. The minus minus will become a plus in the end here. Solving for y prime, you just multiply by y. Well, y is the original function that you started with. So there's that. And then I've got the 9 over 3x squared. This is the 2 over 2x minus 1. This is a minus 6x over x squared plus 4, and the minus minus becomes a plus, and I just chose to write sine x over cosine x as tangent x. Okay. Logarithmic differentiation. You take the log of both sides first. You use the property of logs to break products and sums and powers up into products and, so you break quotients and products into sums and differences, and you write these powers out in front as just being multiplied by constants, and it makes your life so much easier. Okay, I think that's the end of it. So anyway, there's the midterm. If you have questions on any of that, please ask in a discussion or come see me in my office, and we'll fill in some more details if we need to.